Hello, and welcome to the Academy of Useless Ideas. Today we embark on a journey through the mystical realm of topology where we shall delve into the enigmatic concept of compactness. Brace yourself, for this shall be an abstract adventure of epic proportions. At first glance, the definition of compactness may appear to be nothing more than a random assortment of symbols and jargon, leaving you wondering if the mathematicians who conjured it up were simply messing with you. But fear not, compactness is, in fact, a fundamental property that mathematicians stumble upon, and it kept rearing its head in various proofs. It's like discovering a hidden treasure that unlocks a whole new level of understanding. Although the abstract nature of compactness may seem daunting at first, fear not, for it's a concept of great power and usefulness. As we delve deeper, you'll discover how it connects seemingly disparate theorems in mathematics and streamlines arguments. For, as we all know, mathematics is the art of giving the same name to different things, and compactness is a shining example of how mathematicians achieve clarity through abstraction. Who knows, maybe one day you'll even create your own abstract concepts that unite seemingly unrelated fields of study. So let us begin this adventure, and together we shall uncover the secrets that lie within the realm of compactness. Behold, our journey shall be guided by the following abstract yet indispensable theorem. It will serve as a valuable tool for honing our abilities to comprehend theorems and dissect proofs. The theorem in question asserts that in a metric space M, the following three statements are equivalent. Firstly, every open cover of M contains a finite subcover. Secondly, every sequence over M has a convergent subsequence. And finally, M is complete and can be covered by finitely many balls of radius epsilon for every epsilon greater than 0. While this may seem like a mouthful, fear not. We shall break it down step by step so that you can emerge from this journey with a deeper understanding of the mysteries of compactness. In order to learn a theorem, there are two crucial steps to be taken. The first, and perhaps the most vital, is to grasp the statement of the theorem and how it relates to other areas of mathematics. The second step pertains to the technical aspects of comprehending the proof of the theorem. To put it another way, step 1 is akin to viewing the majestic forest from a distance, while step 2 involves venturing down a trail to get up close and personal with the trees. As for this particular theorem, it is rather weighty, so let's us take a moment to fully appreciate its meaning and significance. To gain a deeper appreciation of the forest, it can be helpful to list all the observations that come to mind when reading the theorem. The goal is to ensure that we comprehend all of the different facets of the statement. So, without further ado, here are some key observations and clarifications. 1. It's important to note that subsets of metric spaces are themselves metric spaces, and therefore the theorem applies to any subset of a metric space. This means that the theorem can aid us in classifying both metric spaces and their subsets. 2. The first statement of the theorem pertains to open covers, which can be a somewhat esoteric concept for those unfamiliar with topology. Without a grasp of open covers, it's virtually impossible to make sense of the statement. In such cases, we must pause and delve into what open covers are all about. A cover C of a set M is a collection of sets Ci whose union contains M. An open cover is simply a cover where each element is an open set, and a subcover is a subset of a cover that still manages to cover the whole set. As you can see, the word cover is quite evocative. Indeed, covers can be thought of as covering spaces. The statement tells us that there is some sort of finiteness inherent in the space. No matter how we try to cover it, we can always find a finite subcover. Although this seems quite abstract, it turns out to be a fundamental property of spaces. So significant, in fact, that it has its very own name, compactness. 3. The fact that compactness refers to open covers suggests that they behave nicely with respect to continuity. In fact, the image of a compact set K under a continuous function f is also compact. To see why, consider an open cover Ci of Fk. We can form a cover of K by pulling back every Ci. Since F is continuous, the preimage of an open set is open. Therefore, the cover of K is also open. But since K is compact, we can find a finite subcover. By pushing the finite subcover's elements forward using F, we get a finite subcover of F of K. This property is known as the compactness preserving property of continuous functions, and it is a powerful tool in analysis. 4. The second statement is also important enough to have its own name. A sequentially compact set is one in which every sequence has a convergent subsequence. Therefore, the theorem tells us that compactness and sequential compactness are equivalent in metric spaces. In light of this equivalence, it is not surprising that sequentially compact sets are preserved under continuity. Indeed, let's consider the following direct proof of this fact. Suppose we have a sequentially compact set K, a function f from K to another topological space Y, and a sequence yn over Y. We can construct a sequence in X by choosing xn such that f of yn equals xn. Since K is sequentially compact, xn has a convergent subsequence, xnk, that converges to a point X. Due to the continuity of f, the corresponding sequence ynk in Y converges to fx. This shows that fk is sequentially compact in Y. 5. The last statement is the most concrete of all. A complete space is one where every Cauchy sequence converges, meaning that the space has no quote-unquote holes. The second condition of the statement provides another form of finiteness. A space that can be covered with a finite number of balls of radius epsilon is called totally bounded. Note that totally boundedness implies boundedness, but the opposite is not always true. Can you think of a space that is bounded but not totally bounded? Fortunately, in the real numbers and Euclidean spaces, boundedness and totally boundedness are equivalent. 6. Since the real numbers are complete, any bounded sequence is contained within a complete and totally bounded subset of the reals. By the equivalence between the second and third statements of the theorem, this means that the sequence lies within a sequentially compact set and hence has a convergent subsequence. This is precisely what the Bolzano-Weierstrass theorem asserts, and therefore we can view the theorem as a generalization of Bolzano-Weierstrass with totally boundedness, replacing boundedness. 7. It is also important to consider under which conditions the theorem would not hold. Note that the third statement only applies to metric spaces, as the concepts of completeness and totally boundedness are not defined in general topological spaces. This raises the question of whether compactness and sequentially compactness are equivalent in general topological spaces. Unfortunately, the answer to this question is negative, as there are topological spaces in which compactness and sequential compactness are not equivalent. As mentioned earlier, this abstract theorem simplifies many proofs. For example, we can use the theorem to sketch a proof of the extreme value theorem, which states that every continuous real-valued function f over a compact set K achieves its maximum. Equivalently, the supremum of fk is indeed a maximum. Since K is compact and f is continuous, f of k is a compact subset of the reals. By the third equivalence, that means that f of k should be bounded and complete. The supremum of a bounded and complete subset of the reals is indeed a maximum, and it exists because the set is bounded. Let's call the supremum alpha. For n, we can choose xn as an element of fk between alpha minus 1 over n and alpha. Note that xn exists because alpha is the supremum of fk. By construction, xn is Cauchy and converges to alpha. Since fk is complete, alpha must be an element of fk. Now that we have a better understanding of the theorem's statement, we can delve into the technical aspects of proving it. Once you comprehend a theorem, you may find yourself more motivated to learn how to prove it. It's like looking at a stunning picture of a forest that inspires you to explore the trails within. This video is getting a bit lengthy, so we'll end it here for now. We hope that you feel encouraged to embark on a journey to learn how to prove this crucial theorem.